Okay, so I want to talk a little bit about the system pig, and there's a couple of reasons for this. One is it represents this language layer on top of MapReduce, which I think is pretty important, as I've mentioned before. And it also represents a more direct interface to relational algebra, which I've argued is really the important abstraction from databases. SQL happens to be sort of intergalactic data speak, and is the universal language for programming databases and manipulating data in databases. But really, the secret sauce and the technology that makes it effective is this underlying formalism of relational algebra. And Pig and a few other systems sort of expose this as a first-class citizen. And it's not necessarily the only way to do it, or necessarily the better way to do it, but it does. But since you can see the relational algebra directly, I think it's a nice thing to be familiar with. Okay, and it also, I think, makes the point that you can cherry pick a little bit what features you bring. So while it's very obviously inspired by relational algebra, and of course, if you look in the sort of people that developed it, you can see why. It definitely changes some things about the relational model, and I think that's an important point too, is that we can use this relational algebra abstraction independently of some of the systems that it came from. We can make whatever changes we need and keep what we like and throw out what we don't like. And so I want you to sort of put your relational algebra goggles on and see the world in terms of relational algebra. I think it's pretty effective for working with not just data in general, but especially big data and reasoning about very scalable algorithms. Okay, so fine. So what is Pig? So Pig is an engine for executing programs on top of Hadoop. Okay, so you're going to write a program in Pig, and it's going to generate a sequence of MapReduce jobs that implement that program. Okay, and the language here is called Pig Latin, and it's an Apache open source project, and you can read more about it. Okay, and so why bother doing this? Well, if you're a MapReduce programmer, you're happy with MapReduce, why would you bother doing this? Well, suppose you have data in one file and data from websites in another. User data in one file and website data in another, and you need to find the topmost visited sites by user in a particular age range. And so if you're thinking in terms of SQL, you can probably think about how to express this task as a query. And here's a pictorial representation of it that sort of shows a kind of data flow here. We're going to load users, we'll load the pages, we'll filter by age, do some kind of join on name, group, count up the clicks, order by clicks, and then take the top 5. This may or may not be the way you draw it on the whiteboard if you were to express it yourself, but it's a reasonable way of describing the problem. Well, in MapReduce, there's 170 lines of code, and at least in one example coming from the papers here, it took someone 4 hours to write it. These kind of metrics of how development time are never too compelling, because it kind of depends on their background and their skill set and so on, but still a decent amount of time. While the same program is in Pig Latin is just 9 lines of code and takes, at least in this case, 15 minutes to write. And further, does sort of capture some of this more abstract description of what's going on. Now, this is a little bit contrived because these boxes obviously correspond to sort of particular Pig commands. But I'd argue that this, even people that don't know Pig, if they were to ask sort of what the tasks are in evaluating this English question, they might come up with something along these lines. They may or may not say join, but some of these steps would be present. So I think you could wave your hands a little bit and say that it captures a little bit of the natural language description of the task. Okay, you may or may not buy that. Fine, so here's what it looks like. Load the user data according to a particular schema. Filter the user data based on the age range. Load the pages data. Perform a join. Group. Then you say, well, for each group, count the number of clicks, and we'll talk. This one probably looks the least like relational algebra, and we'll talk about it. And then sort the thing, and then just take the top 5 and store that result into a new file. Okay. And so the point here is that you could also think, well, boy, I could just write all this in Python, right? That'd be much easier. Why do I need to use this new language? Well, the point is that each one of these steps, well, not each one, groups of these steps correspond to individual MapReduce jobs, which mean they scale really, really well, right? It doesn't matter how big your users table is, and it doesn't matter how big your pages table is. This program will work. Okay, so how does the system work? Well, the programmer is going to enter a Pig Latin program by writing these commands. and assigning the results to variables, and then you can refer to the variables in future commands. So this is, we've loaded data into this variable A, loaded data into this variable B, and then you can filter by reference to A and store the result in C and so on. Okay, and then we'll make this point again later, but nothing actually happens. No work is actually done until you try to actually write out the result. So this is sort of what we call lazy evaluation. All right. So fine. So what happens when you write this program? Well, the pig parser will turn the syntax of the program into an abstract representation of the program called an execution plan. And so this is using parlance from databases. And the lead of the pig project is a great database guy named Chris Olson. Okay. So this abstract representation of the plan, these operations that I'm going to call operators, again using database parlance, are sort of one-to-one with the commands, although they need not always be. Okay, but we're not done there. That's just the execution plan. It's still sort of abstract. We can't actually execute that. What we need to do is compile that down into MapReduce jobs. And the gain here is going to sort of be to minimize the number of MapReduce jobs you need, because there's a lot of overhead to executing one of these. So you don't want to run a whole MapReduce job just to filter a data set. You might as well lump that in with other work that you're already doing. As long as you're scanning the data and reading off a disk, you might as well do as much as you can with it. And so, for example, in this case, this program can all be implemented as just one single MapReduce job. In the map phase, you load the data, you filter it, and you also load the other data set. In the reduce phase, you do the join. Okay. And we'll see another example of this a little later on. And then finally, these MapReduce jobs are scheduled on a Hadoop cluster as usual and run as usual. Okay. So these performance results are a little funny, but I still like the argument being made. This is pig performance versus MapReduce. Okay, so this is a little funny because pig is built on top of MapReduce, but the point is that the first version of pig in September 11th, 2008 was a lot slower than just writing the thing raw against MapReduce. But with some various improvements, it got better and better over time until eventually it was just as fast as the handwritten MapReduce. And I think you see this sort of pattern quite a bit, that there is a cost to abstraction, but that you typically can recover a lot of the performance of the hand-coded stuff, meanwhile having gained some measure of programmer productivity by offering a higher level interface. Okay. And so I just like the fact that they actually just bothered telling the story, that admitting that they were quite slow in the beginning and got faster over time. Okay. All right, so what's the data model here? So there's four types involved here. One is the atom, which is just a primitive, right, an integer, a string, and so on. And then there's three different collection types. One is a tuple, and these should be familiar from our first assignment we worked with Python, right? So these three all exist in, well, I shouldn't say that. Actually, bag is a little funny to think about in terms of Python. Let me just say, right, the first is a tuple, which is a sequence of fields, and every field can be of any type. They need not be atoms. Okay. And then there's a bag, which is a collection of tuples, always tuples. But those tuples need not be the same type. So this is different than a table, different than a relation. Okay. And it's a bag, not a set. And, I guess I can ask you, what's the difference between a bag and a set? Well, a bag allows duplicates. Okay. And then the third type is a map, which is a little bit confusing because we're talking about MapReduce, but this is a dictionary in Python, right? So string literal keys map to any other type. Okay. So let's look at an example of this. So what is this thing? Well, it depends on my notation, I guess, but assuming that you don't mind my angle brackets referring to tuple, then you can see that this outer thing is a tuple, and it has three fields. It has a integer, which is just an atom, and then it has this thing, which is a bag, the curly braces I'm going to use to indicate bag. And then it's got this thing, which is a map, a dictionary, that has just one element in it, mapping the key Apache to the value search. Okay. So let's name these guys F1, F2, and F3, and we'll point out in a couple of slides where those names can come from. There's a few different places they can come from, and I'll point out one of those sources soon. But right now, just assume that we have them. Okay. Okay, so let's consider these expressions over this type. So we can write $0, and what that means is give me the first field in the tuple. All right, so in this case, it's just the number 1. We can also access it by name. So if we access F2, that will give us the second field, just because we gave it that explicit name. There's nothing magic about F, nothing magic about 2. And that'll give us a bag with these values in it. By the way, we should say, what are the elements of this bag? Well, they're tuples with 2 integers each. Okay. Now you can also access F2 to give me, so what does this expression do? Well, F2 gives me the bag, and then you can write $0, and I don't love this notation. It's a bit of an abusive notation, but what it means is for every element of the bag, project out the first element. And so this will give me another bag, but it only has 2 and 4 and 5. It has the 0th element of every tuple. Okay. Then you've got this magic hash symbol here, which means find me the value associated with the key I'm about to provide. So look at F3, which is the third field, and hash into it and give me the key Apache. If it's not a map, you're going to get an error. But in this case, it is a map, and so what gets returned is the atom search. Okay. And then you can also write functions. You can say sum up all of these values, and this expression is the same one we saw here, which will be a sequence of integers. And so that'll give you 2 plus 4 plus 5. Okay, and there's a few different other ways to sort of manipulate these things. But the first thing to note is that this is non-relational, right? You've got these nested data structures, and you've got a few different data types.